Hello students, in this video we'll discuss the vertex and edge coloring. Let us first define the vertex coloring. The vertex coloring is a proper vertex coloring of a graph G is a labeling of the vertex set, or it is a mapping of the vertex set to the colors 1, 2, 3 etc. up to K, where the labels are called the colors and no two adjacent vertices get the same color. So it is a mapping from the vertex set of G to the colors which are represented by the natural numbers 1, 2, 3 etc. up to K, where no two adjacent vertices get the same color. So let us consider these three graphs which has the four vertices. So I have here, according to this first graph, vertex 1 is colored with, or vertex B is colored with color 1. Vertex B is colored with color 1. Now vertex A is adjacent to B. So I cannot use the same color 1 to color vertex A. So it should be different 2. Again, vertex B is adjacent to D. Again, I cannot use the same color 1 to color the vertex D. So it should be different, and I can take any other color, say 3. Now, vertex C is adjacent to D. Hence, I cannot use either 2 or 3 to color C. It can be 4 or it can be 1. Color 1, as C and B are not adjacent. So this is a proper coloring with how many colors? 3 colors. Now consider the same graph but with different coloring. So let me color the vertex A with color 1. And here in this color B, vertex B is also colored with the same color 1. But it is adjacent to A. So this is not the proper coloring, it is improper coloring. Let me consider another graph, the same graph with different coloring. So vertex A is colored with color 1. Vertex B is colored with different color 2, as B is adjacent to A. So I cannot use the same color 1 here. Now B is adjacent to D. B is adjacent to D. So vertex D should be colored with different color other than 2. I can use 1, color 1, as A and D are not adjacent. You don't find an edge between A and D. So it should be 1. It can be 1. Now C is adjacent to D. C is adjacent to D. Hence I can color the vertex C with color 2 because C and B are not adjacent, but they are adjacent to A and D, so it cannot be 1. So this is also a proper coloring with 2 colors. Proper coloring with 2 colors. So it's minimum number of colors. Thus, the same graph in the proper coloring, we have used 3 colors here and 2 colors here, right? So one of the important applications of coloring, vertex coloring is the scheduling problem, right? So scheduling problem, we will take it up in the next video. A K coloring is a coloring of the graph using K colors. So we have seen that in the previous graphs, we have used, in the proper coloring, we have used 3 colors as well as we have used 2 colors. So it is a 3 color graph and 2 color graph. So a K coloring is the coloring of a graph using K colors. If a graph is K coloring, then the graph is said to be K colorable. So if just it is the name given, if a graph G is K coloring, then the graph is said to be K colorable. For example, let us consider a path with 3 vertices, 1, 2, 3. So these 3 vertices can be colored with 3 colors. So first vertex with color 1, second vertex is adjacent to first, so I should not use 1, it should be different, so say 2, and the third vertex can be colored with either 1 or any other color 3. It cannot be colored with 2 as it is adjacent to the second vertex. So this P3, path 3 is 3 colorable, whereas the same path 3 is 2 colorable also, because first vertex is colored with 1, second vertex is colored with the color 2, third vertex can be colored with 1, because this vertex, if I name it as A, B, C, C is not adjacent to A. So I can use the same color which I have used for A. So therefore it is 1. So P3 is both 3 colorable and 2 colorable. Now we define what is called as the chromatic number. The chromatic number of a graph G denoted by chi of G is the smallest number k such that G is k colorable. Smallest number k such that G is k colorable. We have seen in the previous example the path 3 P3 is both 3 colorable and 2 colorable. So it cannot be 1 colorable. You cannot use only one color to color these. It's not the proper coloring. So it is both 3 colorable and 2 colorable, but out of 3 and 2, 2 is minimum. So therefore the chromatic number of P3 is 2. Now if graph G is such that the chromatic number of G is k, then we say that G is k chromatic. So here P3 is 2 chromatic. Now let us note down few points. If G has n vertices, then the chromatic number of G should be less than or equal to n. Right? Because you have n number of vertices in the graph G. So it may be like each vertex of graph G are colored with different colors, right? Or it may be with less than n number of colors. So depending on the graph, right? Then second point, the chromatic number of graph G is 1 if and only if G has no edges. So we can color all the vertices with same color. Suppose you have only the graph with only vertices. So all the vertices can be colored with the same color, right? Then let us consider a cycle with 3 vertices, C3. The chromatic number of C3 is 3. So I have 3 vertices A, B and C. So if A is colored with color 1, B should be colored with different color, say 2, and C is adjacent to A as well as B. So it cannot take the color 1 or 2, it should be some other color 3. So therefore the chromatic number of C3 is 3. Whereas chromatic number of any cycle with even number of vertices, so we can call it as chi of C2n. It is 2. The chromatic number of even cycle is 2 because alternate vertices will take the same color. So 1, 2, next vertex is adjacent to 2, this vertex. So it cannot be 2 but it can be 1 as there is no edge connecting these two vertices. So it is 1. Again next the vertex can take the color 2. So it is a cycle of 4 vertices, C4. And if you see C6, it is also a cycle of 6 vertices. Again it will take the alternate vertices will take alternate colors 1, 2, 1, 2, 1, 2. So therefore the chromatic number of even cycle is 2. Whereas chromatic number of odd cycle is 3. Here the C5 we have seen. If you just consider C3 we have seen. C5 if you consider C5, so I can start with 1, color 1, next it should be 2. The third vertex can be colored with 1 because there is no edge between vertex, this vertex and this vertex, and then the next vertex can take color 2, but the last vertex, fifth vertex, is adjacent to both 1 and first and the fourth vertices, so it cannot take either 1 or 2, but it should be 3, and therefore the chromatic number of odd cycle is 3. Let us consider the complete graph. The chromatic number of the complete graph Kn is equal to n. This is very simple because every vertex is adjacent to every other vertex. So therefore the chromatic, and it has n number of vertices, therefore the chromatic number of the complete graph with n vertices should be n. Now if H is the subgraph of G, then the chromatic number of G should be greater than or equal to the chromatic number of H. If G1, G2, etc. Gr are the components of a disconnected graph G, then the chromatic number of the graph G is the maximum of, you just find the chromatic numbers of each component of this disconnected graph, and whichever is maximum, so that is the chromatic number of the entire graph. So maximum of chi of G1, chi of G2 and etc. chi of Gr. Next, consider the chromatic number of the complete bipartite graph K, M, N. So this is equal to 2 because it has two sets of vertices where there is no edge between any two vertex from the same set. So all the vertices from the same set can be colored with one color, and all the vertices from the other set can be colored with the other color. So therefore it is 2. Now what is a bicolor graph? A bicolor graph are those graphs which are two colorable. So it has only two, it can be colored with only two colors. That is, the chromatic number is 2. So there is a theorem which about the bicolor graph. So a graph is bicolorable if and only if it has no odd cycles. If it has no odd cycles, we have seen that the even cycle graph is two colorable. We have seen that the bipartite graph is two colorable, and in bipartite graph we have seen that it is, suppose you have say like this. So this is a bipartite graph, right? K 2, 3, right? This is a two colorable graph because it has no odd cycle. So if you just consider, if you try to find the cycle, it is like this: 1, 2, 3, 4. See, this is a cycle, right? So it is a C4. It's an even cycle, right? Hence this theorem states that a graph is bicolorable if and only if it has no odd cycle. So one of the graphs is bipartite graph. Next, for every graph G, the chromatic number of G should be less than or equal to 1 plus the maximum degree of G. So you know that delta represents the maximum degree of G, right? Then we have a theorem called Brooks theorem. For a connected simple graph G, which is neither complete nor a cycle of odd length, then we have the chromatic number of G less than or equal to the maximum degree of G, right? Suppose you have a vertex which is of maximum degree, so that means those many vertices are adjacent to the particular vertex, and therefore those many vertices which are adjacent to a particular vertex cannot be colored with the same color as the vertex which we are considering, right? So which means that the chromatic number of G should be less than or equal to the maximum degree of G. Now consider the maximum degree of complete graph. Maximum degree of a complete graph is n minus 1, and the chromatic number of the complete graph is n that we have seen. So here we have seen that chromatic number of Kn is less than or equal to chromatic number of Kn is less than or equal to the maximum degree. So degree of Kn, maximum degree of Kn is n minus 1 and chromatic number of Kn is equal to n. So if you substitute that in this equation, that is n is less than or equal to 1 plus n minus 1. So n is equal to n. So equality in this case we have seen. Similarly, the chromatic, the maximum degree of any cycle for that matter, any odd cycle is 2 and the chromatic number of the odd cycle is 3. So this is also we get the equality, that is the chromatic number of G is equal to the maximum degree of G. Now it was it was proved that for every planar graph we have chromatic number of G less than or equal to 6. So this theorem is called 6 color theorem. So initially it was proved that every planar graph can be colored with at most 6 colors. 6 color theorem. Later it was proved that every planar graph can be colored with at most 5 colors, one less than the previous one. So it is called 5 color theorem. Later, using computer, it was proved that for every planar graph we have the chromatic number of G is less than or equal to 4. Right? So these are the 6 color theorem, 5 color theorem and 4 color theorem. So let us consider a graph with vertex set V and edge set E. Now we'll see what is chromatic polynomial. Given a connected graph G and lambda is nothing but the number of different colors. So let us find the number of different ways of properly coloring the graph G with these lambda colors. So you have a graph G with say n number of vertices and you have lambda number of colors, different colors. So in how many ways you can color the graph G with lambda colors? So let us consider a null graph. Consider a null graph n with n number of vertices. Since since no two vertices are adjacent, null graph means it is a graph with only vertices, no edges. So a proper coloring of this graph can be done with only one color, single color to all the vertices. Thus, if there are lambda number of colors given, then each vertex has lambda possible ways of coloring and hence we have the graph can be colored with lambda power n number of different ways, right? So suppose you have n number of vertices in the null graph. The first vertex has lambda number of ways of coloring. Second vertex also has lambda number of ways of coloring because they are not adjacent, so I can use any color out of lambda colors. So like this, if you color all the n number of vertices, there are lambda power n different number of ways of coloring the null graph with n vertices. Consider the complete graph Kn. In this graph, every two vertices are adjacent and requires at least n number of colors for the proper coloring of the graph, right? So we have seen that the chromatic number of Kn is n. Every vertex is adjacent to every other vertex, hence it requires n number of colors for the proper coloring of the graph. Suppose if there are lambda number of different colors available, then number of ways of proper coloring of Kn is 0 if lambda is less than n. If you have the number of colors less than the number of vertices of the complete graph, then somewhere you will have to repeat one or two colors. You have to repeat for the adjacent vertices, but it's not a proper coloring and therefore it is 0, right? Next, and the number of ways you can color, number of ways, if there are n number of colors to color Kn, then it is n factorial ways. It's not one, it is n factorial ways, because I can color the first vertex with lambda number of ways, second vertex with lambda minus 1, third with lambda minus 2, because they are adjacent. If you consider any vertex, they are adjacent to each other. Each vertex is adjacent to all other vertices. So I have to use different colors only. So therefore it is n into n minus 1 into n minus 2. So if instead of lambda I should write n into n minus 1 into n minus 2 etc. 2 into 1. So it is n factorial ways. Suppose if lambda is greater than n, then it will have more than one number of ways. So let us see that how it is. Yeah, whatever I just told here is written here. Okay, so if v1, v2 etc. vn are the vertices of the complete graph n, then v1 can be colored in lambda number of ways. v2 can be colored with lambda minus 1 number of ways or colors, because already I have used one color. Then v3 has lambda minus 2 colors, and so on, vn with lambda minus of n minus 1 colors. And the product will give you the number of different ways of coloring. So it will be lambda into lambda minus 1 into lambda minus 2 etc. lambda minus n plus 1 number of ways I can color the graph Kn with lambda colors which is greater than n. Okay. So the number of different ways of properly coloring a graph G with lambda number of colors is denoted by P of G comma lambda. Hence, whatever we discussed now can be put like this. The P of Kn minus lambda is equal to 0 if lambda is less than n. Then, number of ways of coloring a complete graph n, Kn, with n number of colors is n factorial. Then, P of Kn comma lambda, where lambda is greater than n, is lambda into lambda minus 1 into lambda minus 2 etc. lambda minus n plus 1. Then null graph with n number of vertices. P of n is n comma lambda is lambda power n. Now P of k1 comma n. So this is a bipartite graph with one vertex in one set and n number of vertices in the other set, right? So you have lambda number of lambda colors. So if I use the first color here, right, then I have so how many possible ways I can color the vertex in which is only vertex in the set. So I have lambda number of ways of coloring this. So next, this vertex should be colored with lambda minus 1 colors. I have lambda minus 1 number of ways of coloring this vertex. And since there is no adjacency between these two vertices, I can also color with any color, right? So therefore, this is also with lambda minus 1. Remaining all vertices can be colored with lambda minus 1 number of colors. Therefore, it is lambda into lambda minus 1 to the power n minus 1. So provided if lambda is greater than or equal to 2. Now, what is the probability of Ln comma lambda, or you can also write it as Pn, the path, Pn comma lambda. So Pn, again, let me consider the path with n number of vertices, right? So the first vertex is colored with say lambda. Second vertex has the possibility of coloring with lambda minus 1, okay? And the remaining, the third vertex should not take this color whatever you have used for the second vertex, but it can take the first color. So again it has lambda minus 1 number of colors. Similarly for all the other vertices, again it is lambda into lambda minus 1 to the power n minus 1 if lambda is greater than or equal to 2. So in each of these, if you observe, each of these cases, p of g comma lambda is a polynomial in lambda. So this p of g comma lambda is called the chromatic polynomial. So if g is made up of n parts, say g1, g2, etc., gn, then the chromatic polynomial p of g comma lambda is given by the product rule. So p of g comma lambda is p of g comma g1 comma lambda into p of g2 comma lambda into p of gn comma lambda and so on. Right? So there are few theorems on this chromatic polynomial. Let us state these theorems. A graph G with n number of vertices is a tree if and only if the chromatic polynomial p of g comma lambda is lambda into lambda minus 1 to the power n minus 1. So we know that a tree is an acyclic connected graph. Acyclic connected graph. So it can be colored with in how many ways? It is lambda into lambda minus 1 to the power n minus 1 ways. We have another theorem which states that let u and v be two non-adjacent vertices in a graph G. Let G plus E be a graph obtained by adding an edge between u and v. Let G into E be a simple graph obtained from G by fusing the vertices u and v together and replacing the sets of parallel edges with single edge. Then p of g comma lambda is equal to p of g plus e comma lambda plus p of g into e comma lambda. This is very important theorem which is used to find the number of ways a graph can be colored with given lambda number of colors. Okay, so this can be seen in an example. Whatever the theorem we have stated now can be it is applied to a problem. Let us see how. So find the chromatic polynomial of the following graph. So graph G is given, which is with 4 vertices and 5 edges. Okay, so let us apply the above formula or the theorem. So what does the theorem states? If u and v are any two non-adjacent vertices of the graph, then G plus E be the graph obtained by adding an edge between u and v. So u and v are non-adjacent vertices. You make them adjacent by adding an edge E. Right? Now, on the other hand, you just fuse those two vertices u and v, right, and make it a single vertex. Remove all the parallel edges. So that is your G into E. So when we apply that, yeah, this is what we get. Now here we have seen that, let me just call it as A, B, C, D. A, B, C, D are the vertices of the graph G. Now we have here A and C are non-adjacent vertices. So we are going to draw a edge, right, between A and C. So that is your G plus E. Now it became A, B, C, D with this edge. Now what do you mean by G into E? Fuse A and C, right? Fuse A and C. So you just combine this C with A, right? So C became A now. Then you are left with the B and D. And the adjacent edges, incident edges will go off, right? CB and CD will go off and it is just this triangle. Now we are getting K4 and K3. So once you are end up with a complete graph or a cycle, right, then it is very easy to write the number of ways of coloring those graphs, right? So it is P of G comma lambda is equal to P of K4 comma lambda plus P of K3 comma lambda, right? Hope it is clear. Now we know that a complete graph with lambda number of colors can be colored with lambda into lambda minus 1 into lambda minus 2 etc. lambda minus n plus 1, right? So this product will give you the number of ways the K4 can be colored with lambda colors. Similarly, P of K3 comma lambda. K3 comma lambda is lambda into lambda minus 1 into lambda minus 2, right? So when you simplify this, lambda into lambda minus 1 into lambda minus 2 is a common factor. So you are left with lambda minus 3 plus 1. So it is lambda minus 2. It becomes lambda minus 2 square, right? So it is very simple to find the number of ways a graph can be colored with lambda colors using the above theorem. So let us apply this for the next problem. Find the chromatic polynomial of the following graph if 5 colors are available, right? There are 5 colors given, okay? You have to color them for this graph G. You have 5 vertices V1, V2, V3, V4, V5, okay? So this vertex, there is an edge between V2 and V5. Now let us follow the same procedure. Yeah, we see here V5 and V3 are not adjacent. V5 and V3 are not adjacent. V2 and V4 are not adjacent. So in the first step, what I do is I will add an edge between V3 and V5 to get G plus E, right? Next, so those two vertices are fused, right? So that means V5 will fuse with V3, so it becomes a V3, and whatever the edges incident to V5 will go off. That is, this edge will go off, this will go off, right? This is cancelled, and anyway, this is the new edge which we have included, that will also go off. So this is what we get. This is G into E. Now this is not any complete graph. Till we get the complete graph or a vertex, a single vertex, or a path, or a two vertex path, if we get, then we stop the procedure, right? So now till then we have to continue this. Next, consider this G plus E. This is one graph. Now again continue the process. Here we see that V2 and V4 are not adjacent. V2 and V4 are not adjacent. Hence I will add an edge to this. So it becomes G plus E, right? When you add an edge, those two vertices are to be fused, right? So V4 and V2 should be fused. So it is V4, V2 is fused with V4, so it became just V2. Now you have V1, V5, V4, V3. Because V2, the edges incident to V2 are this edge, this edge, this edge, and obviously this edge. So these are cancelled, deleted. And now we are getting a complete graph with 4 vertices, K4. Now if we come to this point, this G into E again, here we see that V2 and V4 are not adjacent. So include an edge, G plus E, include an edge between V2 and V4. So G plus E. Now V2 and V4 are to be fused. So V2 will go off and the incident edges will also go off, and you will get a K3. So thus in this step we are getting all complete graphs, and therefore polynomial chromatic polynomial P of G comma lambda is equal to P of K5 comma lambda. This is K5, this is K4, this is K4, and K3. So P of K5 comma lambda plus P of K4 comma lambda plus P of K4 comma lambda plus P of K3 comma lambda. So this is 2 times P of K4 comma lambda. Now when you by applying the formula, it is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 into lambda minus 4 plus 2 times lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 plus lambda into lambda minus 1 into lambda minus 2 for K3. Now since there are 5 colors given available, so we take 5 G of 5 is equal to, this lambda into lambda minus 1 into lambda minus 2 is nothing but 5 factorial plus 2 into 5 into 4 into 3 into 2 from this term, and from the last term we get 5 into 4 into 3. It is 420 number of ways. Right? So this is how we find the number of ways of coloring the graph with the given color, with the given lambda number of colors. Let us now define the edge coloring. Edge coloring of a graph is an assignment of colors to the edges of the graph so that no two adjacent edges have the same color with the optimal number of colors. Okay, here I have the graph here. So first I will consider this edge. Let me call it as E1, E2, E3, E4, E5, E6. There are 6 edges. Now I have to color these edges in such a way that the colors are not, we cannot use the same color for the adjacent edges, right? As well as we have to use minimum number of colors. Let us see. So suppose if I color the edge E1 with purple color, right, I cannot use the same color for the edge E2. It should be different. So I have used green color. Now edge E3 is adjacent to E2 but not adjacent to E1. Correct? So I can use the same purple color. Then edge E4 is adjacent to E3 and E1, E5. So but not adjacent to E2. Hence I can use green color. Edge E5 is adjacent to E1 and E2. Hence I cannot use the purple and the green, but I can use yellow color. Edge E6 is adjacent to all the vertices E1, E2, all the edges E1, E2 and E5. So I should take different color, say blue, and therefore this graph needs 4 colors, right? So 4 colors are required here. Now a K edge coloring is the proper coloring if adjacent edges have different labels or colors. A graph is K edge colorable if it has the proper K edge coloring. Just like how we defined for the vertex, the same holds good for edges also. Then the edge chromatic number, or it is also called as the chromatic index, denoted by chi dash G of a loopless graph G, is the least K such that G is K edge colorable. So now in this example we have seen that we used minimum number of colors to color. I can use 6 different colors. 6 different colors. I can also use 5 different colors to color this graph, which becomes a proper edge coloring. But I can also use only 4 colors to color this graph. So the minimum number of colors used is 4 here in this. Hence it is a 4 edge colorable, right? So chi dash of G in this case will be 4. What is the edge chromatic number of the graph G, right? So we have this graph. Let me start from the edge E1. Okay, let me call it as E1, E2, E3, E4, then E5, E6, E7. Okay, so let me color the edge E1 with 1, first color. Okay, so E1 is adjacent to E2. I cannot use the same color 1, so it should be 2, different. E4 is adjacent to both E2 and E1. So I cannot use first and second color, but it should be the third color. E3 is adjacent to E2 and E4 but not adjacent to E1. Hence I can repeat this color 1. Similarly, for E5 I can use 2. E7 I can use 3 because E7 and E4 are not adjacent. I can use the same color. E6 is not adjacent to E1, hence I can use the same color 1. So therefore, with minimum number of colors, we have colored the edges and the chromatic index of the graph G is 3. Okay, so a few points. The chromatic index of G is greater than or equal to the degree of G, maximum degree of G, where delta of G is maximum degree of G. So chi dash of Kn is equal to n. So it's nothing but the chromatic index of a complete graph Kn is n if n is odd, and it is n minus 1 if n is even. Okay, for example, we consider say complete graph with 5 vertices, right? So yeah, if I use the first color for this, right, I cannot use the same color for the incident edges which are incident to this vertex because they will be adjacent edges. So it should be 2, 3, 4, right? And this vertex, this edge 1 is also adjacent to this vertex. So it should be, I cannot use again this edge is adjacent to 1, adjacent to 2, adjacent to this edge, right, as well as this. So I can take say 4 or 3. I can use the color 3, right? Then this is adjacent, this edge is adjacent to 1, this edge is adjacent to 2, also adjacent to 3. So I can use 4. Now if you consider this edge, it is adjacent to 4, it is also adjacent to 3, it is adjacent to, so 2 is adjacent to this, but this is not adjacent to this, so I can use 3. This is just a minute, 2, so this edge is not adjacent to this edge, so I can use 2. Right, now if you consider this edge is adjacent to 4, it is adjacent to 3, it is adjacent to 3, it is also adjacent to 2, so this should be 1 and therefore it is 5. So 5 colors are required to color odd complete graph. Similarly, if you can check that for even complete graph, it is n minus 1. Next, the chromatic index of this cycle Cn is 2 if n is even and 3 if n is odd. Then the chromatic index of the path Pn is 2, right? Then few points again. For a bipartite graph G, we have the chromatic index of G is equal to the degree of G, maximum degree of G, right? Then for a complete bipartite graph Km, N, we have the chromatic index of Km, N is equal to maximum of M, N. Then if G is a simple graph, then the chromatic index of G lies between delta of G, that is maximum degree of G, and maximum degree of G plus 1. So these are few important theorems whose results are very important. So thus we discussed the edge coloring. We'll see the application in the next video. Thank you.